We're going to talk, actually continue our conversation about direct measurements, indirect measurements, and we're actually going to do some worked examples to kind of basically clarify and kind of really see how you essentially apply these concepts and these kind of processes in real life experimental measurements and experimental methods and techniques. So just a quick review. So direct measurement processes were pretty straightforward. So you take your measure and you compare it, we input it here, we do our comparison, we compare it to standard, that's the process of measurement, and we get our readout. So direct measurements, fairly straightforward, easy to do. Unfortunately for us, are a little bit less, are more uncommon. The reason being, again, we are looking for high precision, high resolution in our experimental apparatuses. Where, for example, if you're working with materials and you're doing a graph of intensity versus 2 theta of an XRD measurement, and you see kind of peaks here of different metals, and you're trying to measure the lattice parameter A, see if it's whether it's BCC, FCC, simple cubic, etc. If you're taking my Engineering 45 course, you know this exactly. We're looking at making measurements in the nanometer length scale. We can't do this directly measuring against a ruler. So that's kind of the process where direct measurements are a little more uncommon. So instead, we're going to be dealing with indirect measurement processes. So indirect measurement processes, as you can see here, have 3 stages. So we talked about it last time. You have your measure and your input. You can have this kind of calibration input. We'll see a couple of examples today just to kind of calibrate your apparatus. Then we have stage 1, which we have our sensor transducer stage. So we convert our signal into some type of analogous signal. So we transduce. So a lot of times that's going to be an electrical signal. We'll see some kind of other examples today. Then you have stage 2. We have our signal conditioning stage. So this can be anything from amplification, filtration, and really any type of mathematical operation. And really you're basically convert back to measure and. And then finally, stage 3, we are going to be doing our readout stage. So again, this could be an Excel file, a text file, readout on a computer, a graph, etc. So that's kind of the 3 stages that we're going to have to kind of look at and diagnose. And so when we're thinking about measurements and doing measurements and making measurements or designing an apparatus, we have to kind of think about these 3 stages and how do we minimize uncertainty in our measurements and improve. We want our resolution to be very high. High resolution. Excellent. So let's go ahead and actually do some examples like I promised last time. So let's first think about the first lab that we are actually going to do in our course, which involves basically using a thermocouple to measure basically temperature in different environments. So we're going to have basically beakers. My drawing skills aren't great, and so we're going to have basically here, beaker here filled with ice. I should put this here. I should change to blue, but you get the picture. So you have ice here. So we are going to actually create our handmade thermocouple, and we're going to make a T-type thermocouple made of copper. Copper, constant. So what happens here is you put basically you kind of connect the wires, and you'll have basically your DAC over here. So you'll have your copper wires going into the DAC over here. You'll have kind of like this sensing junction that goes into here, your reference. So this is the reference junction, and then here you'll have your sensing junction, and then they wrap around here. So let me. The diagram below is going to be much more helpful, as you'll see in just a second. So this is kind of the schematic I'm trying to kind of draw here. So again, we have this, what we're going to call here, this is going to be our reference junction. This is going to be our, basically your sensing junction here. This is your sense, and then this is going to be our readout in the volt, how we transduce our signal into the voltmeters. Don't want to give away the secrets just yet. So what happens in a thermocouple? Thermocouple is actually a really kind of super interesting material science kind of topic in and itself, because it has to deal with basically something called the thermoelectric effect, also called the Seebeck effect, or the scientist engineer who figured it out, Seebeck effect right here. So what happens is when you have two dissimilar metals that are under a temperature gradient, so if you have two different metals, so if you have that kind of sensing junction, so one type of metal, another type of metal, and if you expose that to a gradient in temperature, gradient symbol, it will produce a change in voltage. And that change in voltage is governed by this kind of Seebeck equation, from the Seebeck effect. So a gradient in temperature creates a gradient in voltage. So that's kind of the basic fundamental principle. This is S is called the Seebeck coefficient, and it varies depending on what type of thermocouple you use. So what type of metals, again, it depends a lot on the kind of the thermal properties that you're dealing with. So that Seebeck coefficient will change. Seebeck coefficient can also be a function of temperature as well, although usually you kind of see it represented as a constant. So that's kind of the fundamental equation and the kind of the concept behind how a thermocouple works. So that's how we're able to, again, if you're using a glass thermometer, for example, a glass thermometer, even the general ones that you'll kind of see and find around there, what's the resolution there? Well, I mean, you have your glass thermometer. It has kind of basically these lines. Really, you have basically plus or minus 1 degree C that you're working with. But if you want higher resolution, again, this is why we need this kind of indirect measurement process. We need to kind of convert to some analogous signal. But again, I'm getting a little bit ahead of myself. So let's go ahead and develop and build the indirect measurement process for a thermocouple. So let's look at my diagram that I made over here. So cover your eyes and don't look. So what is our measurand? Our measurand here for the indirect measurement process is temperature. What are we trying to measure in this process? We're using a thermocouple to measure temperature. What is our sensor transducer stage? What are we converting our signal? Well, our temperature is converted to voltage. That's kind of the whole, again, the process of that thermocouple. Ignore this calibration step for a second. We'll come back to that. We've done stage one. So our conversion, we've transduced our input, our measurand right here, our input, into voltage using our sensor transducer device, which was that thermocouple. So stage two now is the signal processing. So what are some kind of possible scenarios or signal processing steps we could take for this voltage signal, this electrical signal? Well, you could amplify the signal using basically a power amplifier. Why do we want to amplify our signal? Well, amplify your signal, you're going to increase your signal to noise ratio. So if you amplify that signal, you're going to be able to kind of filter out and get rid of some of the noise in your measurements, and again, improve essentially the quality of your data, the precision, the resolution, et cetera, et cetera. You could also do filtration. That's not as common, I think, for thermocouples, but again, that's a possible step. So you could filter out if there's any kind of, again, if there's some high noise or high frequency noise in your voltage data, for example, for some reason, you could filter out that. This filtration step is going to be very important for in just a second for basically DFT, discrete Fourier transforms. So, and then what's the last kind of step? What's the mathematical operation that we're going to use to get back? So again, we've converted temperature to voltage, but again, we want our readout to be temperature. Well, we're just going to use our Seebeck equation, our exactly, our change in voltage related to change in the gradient temperature. So we'll solve essentially for the change in temperature and get temperature. So in stage three, our readout, it could be a temperature on a multimeter, it could be a readout on LabVIEW, it could be a data file. Basically, it's whatever you want to work with. Usually, again, we're always going to be working with data files. You can build in, again, into your experimental apparatus, basically your data analysis, so it's done automatically. But again, usually we're measuring something and then we kind of figure out and perform the analysis afterwards, after you do the experiment. that's your first indirect measurement process. Congratulations. Now you're ready for lab in a couple weeks. So yeah, that's kind of the first step. So no big deal, right? All right, let's move on to the next example. So now what we're going to do is a really fun experiment. So what we're going to do is we're going to work with a cantilever beam. So hopefully you remember your mechanics of materials and your cantilever beam equations. And what we're going to do is we're going to fix one end, so fixed end cantilever beam. We are going to place an accelerometer. I'll put that right here. Accelerometer on the end of our beam, and we are going to apply some deflection here. The beam is going to kind of bend. We're going to bend it. We're not going to plastically deform it. Then we're going to remove the load. So remove, and then the beam is going to kind of vibrate, and basically vibrate freely. So what do we want? But what we want to measure is, depending on the length of this beam, so we want to figure out what is the resonant frequency of that beam. That's going to be kind of the critical thing that we are going to look at in this lab. So let's go ahead and get get to it. So what are we? What is our measurand? What are we trying to measure in this experiment? Well, we're going to measure the resonant frequency of our beam. That's going to be, again, that's always our input. Oh, sorry. Going back slightly, I forgot about myself. What is this ice bath reference in our thermocouple experiment, if you're doing a handmade thermocouple? Well, if you want to calibrate you could calibrate, if you had an unknown thermocouple, let's say we didn't know it was a T-type thermocouple. If you wanted to calibrate and figure out what is your seebeck coefficient S, you could do this, what's called a 2-point calibration. So you can basically look at the voltage as a function of kind of the temperature here. So you could make two measurements. So you can put your sensing junction here, this sensing junction, you can put it right in the ice bath. So you can measure a temperature at like 0 C, for example, and you can measure a temperature at, let's say, 150 C, and you could look at the voltage that corresponds to this temperature, look at the voltage that corresponds to this temperature. You could do a fit. So this is a 2-point calibration. Not the best. Ideally, you'd want to see different points kind of along here. So multi-point calibration, the more points you have, obviously the better your fit. You can kind of make sure that indeed this looks linear, or maybe it could, again, look exponential or logarithmic, or it could look, kind of very, very strange, erroneously, who knows. That's why you want to take multiple points. But if you do this calibration, then you can figure out and calibrate your apparatus and figure out the seebeck coefficient. Quick question. If you do this calibration from 0 to 150 C, can you use the equation that you developed to figure out the seebeck coefficient to measure something at 200 C? No, absolutely not, because we don't know. Once we calibrate, once we fit this curve, we know what this curve looks like from here to here. But who knows over here? It could be a delta function. It could go exponentially. It could, drop off. It could do some, crazy things outside there. So we're only confident using this expression within these bounds of our multi-point calibration. So sorry for that tangent, but it's an important tangent. So back to our problem with the frequency of an aluminum beam. So we want to measure what is the resonant frequency of that beam. So the vibration, and we want to see what's that frequency of that beam depending on the length and how it changes as a function of length. So let's go ahead and figure out what we're going to kind of let's draw our again indirect measurement process diagram. So this is a better figure. We're going to go right here, and so our input here is going to be frequency, and then we are going to move. So our input's frequency. We are going to put here. See, there really isn't. The calibration step here. There really isn't one. You could, again, there could be a calibration step where if you have like a beam that's very well characterized of a length, you could kind of calibrate your results. But again, you actually don't really need the calibration step here as long as your accelerometer is calibrated. So we are assuming that accelerometer, that is working fine. So that's an assumption that we make here. So what's our sensor transducer step? So we want to measure frequency. We're going to convert that frequency to acceleration. So we are going to get a plot of acceleration, undo that. Acceleration versus time, and you're going to see basically kind of this type of signal, an output. So that's our transducer step. So we're going to convert, again, frequency to acceleration via our accelerometer. Now, what is going to be our signal conditioning stage? Well, you can amplify that signal. That's definitely, again, possible. We want this acceleration data to be clean. We want high signal noise ratio. We want to kind of really be able to see the distinctions, distinct values that kind of differentiate, how this curve in kind of the sinusoidal or this kind of periodic pattern, how it changes. So we could definitely amplify the signal. Filtration is very important. A lot of times you could have basically high frequency and even low frequency noise. Or, for example, there's a really cool, when we get to Fourier analysis, EKG machines. The things that you kind of see on TV shows with that like doot, doot, making those noise. That's actually a discrete Fourier transform of voltage measurements from actual cells in your body. So when they put those kind of like paddles or these kind of circle things, and they attach it to your chest, you're actually measuring the voltage generated from cells in your body. It's unbelievable. We'll talk a lot more about that when we get to Fourier analysis. But that's actually a Fourier transform. But it's so messy. Like you can imagine, like the distance between where your chest is and then the cells in your body, you're going through a lot of like nasty junk in biology. So you actually have to filter out, and you want to kind of target, your heart rate. Hopefully your heart rate's like 40 to 70 BPM. So you could actually filter out any kind of signals that aren't in this range to kind of improve this EKG result. But anyway, so filtration is definitely, for discrete Fourier transforms, definitely possible. And finally, we need to use our, again, you'll see these guys very, very soon. We're going to figure out our harmonic coefficients, and we're going to perform basically a discrete Fourier transform to go from, again, our time space into inverse time or reciprocal time space, which is frequency. Because frequency, omega equals inverse time. We want our values in hertz. Yep. So again, we're converting back. We'll get basically a plot. Let me scroll down here for a second. We're going to get a plot of what's called our frequency spectrum as a function of omega, and you'll see basically nothing, 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 and then boom, a big spike. And then that dominant frequency, the largest amplitude, is going to be our resonant frequency. So that's how we're going to calculate, and again, get back. So we went from frequency to acceleration. We'll take acceleration and go back to frequency here, omega f. We're going to use f a lot in this class. We're looking at cyclical, not rotational frequency, or frequency, not rotational frequency. Anyways, our last stage is just going to be this kind of readout, and then we'll figure out and read our frequency spectrum and our resonant frequency from here. So that's quickly in a nutshell our what we'll be doing actually in lab. Again, unfortunately with remote teaching, you're not going to be able to actually deflect the beam, but you're going to analyze the data. You're going to perform a lot of Fourier analysis. Get ready to code this in Mathematica, but it's going to be really fun. And once you develop this code, it's super useful much later on in your life. So the last experiment or kind of process we're going to talk about today is basically one of our last lab, which is mechanics-based lab. And we're going to deal again with our old friend, that aluminum beam. So we're going to have, again, a fixed kind of cantilever beam, but this time we are going to attach, we're going to apply load. Cantilever beams, you can't get enough of them. But we're also going to apply strain gauges. So we are going to connect this into a circuit called a Wheatstone bridge. So Wheatstone bridge basically is kind of this forearm. So let me try to draw it here. You create a circuit. We're going to work a lot with this in some standard configuration. 1, 2, 3, 4. And you basically, again, measuring strain, if you're trying to generate this stress strain curve and deal with all these kind of stress tensors. Everyone should know this from ENGR 45, your good old friends. Why is this tensor symmetric. Hopefully everyone remembers. If not, we'll have a good rotational. You can't have, we're assuming our objects are not rotating. So by that, by the conservation principle, you have to keep that guy. This has to be symmetric. Anyways, also what the strain tensor will be as well. But you, again, to measure these strains, which are extremely, extremely small, especially for metals, we cannot use our eye. We cannot use a ruler. We can't use those values. We need higher resolution. So to do that, again, we're going to convert our signal, which again is this load, this strain. We're applying a physical strain to our material, and we're going to convert that to this, again, this Wheatstone bridge, this electrical signal, and we're going to kind of compare and use this fundamental equation of this output voltage that we measure as a function of the excitation voltage over the gauge factor over 4 times the strain in each arm of this strain gauge, or of this, kind of Wheatstone bridge configuration. Again, much more on this later, but again, but let's focus on kind of the general process of how we analyze and measure basically these kind of, again, different experimental processes. So what's our measurand? Well, it's going to be strain, as you might anticipate. This is just a nice picture. We'll come back to this a little bit later. I really like it. Tension extending the wires, compression compressing the wires, and it's going to lead to lower and higher resistances. I have lots of little fun demos. I'll probably record myself pulling this little piece of rubber. So look forward to that. So what is our generalized measurement diagram here? So our input is going to be strain. We're going to convert the strain to voltage via our strain gauge, which has those kind of wires and resistance. So as those wires change length due to the strain, there's going to be basically this change in voltage that is related to the equation over here. What's our signal processing step once we've converted to this electrical signal once again? Well, exactly. You can amplify it, filter out noise. All those are possible. Filtration's not as common, but you can do it still. But then again, the fundamental equation, how do we get back from voltage? We went from strain to voltage. We want to go back to strain. Well, we're going to use this. These are what we measure, or what our readouts are, delta V naught, VI, F is a constant. So we'll solve for what is our strain. And the readout is, again, as you might anticipate, it's this kind of, document or text file or data set. So that's basically all there is to it. Now, there is this really kind of cool and actually probably a little bit hidden calibration step. So one of the things is once you apply the strain gauge, oftentimes, because you have to push down really, really hard on that strain gauge with your thumb, often you'll pre-strain the material. So remember, this is the change in the voltage. So even when there's no strain in your material, so on our beam, we have our strain gauge. Even if I don't apply a load, so if I haven't applied, my load is 0, there's still going to be basically, when you look at your Wheatstone bridge, some small voltage that is basically an output. Usually, again, that's due to pre-strain and some other kind of, talk to your circuits professor, and we could talk to you about that. But anyways, so you have to kind of normalize and basically create that baseline from, okay, we're looking at that change in that output. So it's a small calibration step, but again, an important one. If you don't do that, if you don't calculate that change, then it's we could be in big trouble in terms of actually the values that we calculate. So yeah, so those are some, hopefully those kind of clarify and remove some confusion or any potential confusion from these indirect measurement processes, and hopefully they've been a little bit fun. You'll have more practice on your problem set, obviously, of course, working with these. And next time we are going to talk calibrations, kind of talked about a little bit here. We've already hit that multi-point calibration and talked about those experiments. Next time we'll get a little bit more into basically error and uncertainty, bias, error, precision error. We're going to talk a lot about that in the course later on. But really, we're going to focus on, again, a lot of this, especially with remote teaching and in general in my course, whenever we have a lab component, we focus heavily on technical writing, because technical writing and communication is critical. Whether you go in industry, academia, wherever you go in life, you need to be able to communicate this technical information, which is very, very technical, very, very difficult. It's hard enough to kind of communicate that with your colleagues and friends that are experts in that area. And it's a whole nother kettle of fish when you're trying to explain that to someone. Again, I don't want to demean like business people, but it's really difficult to talk to business people about discrete Fourier transforms and why they're beautiful and important and awesome. But it's part, you have to be able to communicate that information. So we're going to talk about all different types of technical writing next time. We're going to talk about how you want to present and graph your data, and you're going to talk about line fitting and how to design our experiments. So a little bit of that next time, and then we'll be done with lecture 1. And congratulations. And then we'll get finally into what everyone's been asking for, the math. So statistics is coming. Don't worry. You'll be careful what you wish for. There's going to be lots of data analysis, Mathematica, and fun things to kind of analyze in terms of that uncertainty. So yeah, I'll talk to you all next time. Thanks. Bye.